The best way to get ready for an exam is to practice, because we want to become comfortable with problems, we want to have experience doing problems, and we often see the same kind of ideas show up again and again. So if we can do the old exams, then it's a good sign that we'll be able to do the next exam. And we just don't want to do the exam, we want to do it great. And so that's our goal. So let's go ahead and do some problems. And so in particular here we have our old exam. This is the Math 166, also known as Calculus 2, Exam 1 from fall 2022. Looks like we're going to get to do 7 problems, so we're going to have some fun. And well, I guess the first thing for us to write down is our name, because, well, you won't get credit if you don't put your name on the exam. And we'll put answers as our name. Well, let's get going. So our first problem. A solid lies between planes perpendicular to the x-axis at x equals 0 and x equals 1. Okay. Each cross-section perpendicular to the x-axis between these planes is a rectangle whose base runs from the x-axis to the line y equals 3x plus 1, and whose height is half the length of the base. Find the volume of this solid. Now, this is going to be one that the hardest part about this problem is just unraveling what's going on. We know that we're after a volume. Now, this particular solid is not a revolution one, and so what is going on here is we're describing cross sections. And so in particular, this is the variation where we want to find the integral a to b, the area of that cross-section dx. So that's the volume formula that we're building off of. And the hard part is, what is that area function? Okay, so we have to go through and start unraveling what all these little bits and pieces mean. So let's start here. A solid lies between planes perpendicular to the x-axis at x equals 0 and x equals 1. So we'll start here. We have x equals 0 and we have x equals 1. And okay, so we're starting at 0 and we're going to 1. And now it says if we have a cross section perpendicular to the x-axis, so all right, we're going to just draw a cross section here. So we have our plane that's perpendicular to the x-axis. We want to say, well, what does it look like? And we're told it's a rectangle. Now that's good news for us, because area of rectangles is not too bad. The area of a rectangle, base height. So we have to figure this out. And so there's a rectangle whose base runs from the x-axis to the line y equals 3x plus 1. Okay, so here's x equals 0 and x equals 1. So we'll sketch in our axis here. So let's say this is 1, and we have y equals 3x plus 1. Then what we have is that at our slice, this right here is our base. So the base runs from the x-axis to this line. So here is our base. Good. Now what's our height? Well, what do we have? It's a rectangle, right? So the hardest part is we're running out of colors to make sure we understand our picture. So we need to know our height, and it tells us that our height is half the length of the base. Okay, so what's our base? Let's write things down. So the base is from the x-axis to the line y equals 3x plus 1, so that's 3x plus 1. And then our height is 1/2 our base, and so that's 1/2 of 3x plus 1. And so we put everything together, and we say, okay, to know the area of a rectangle, it's base times height, so our volume is the integral a to b of 1/2 of our 3x plus 1 times 3x plus 1 dx. So this is our a of x equals base times height. Okay, so that's the setup. And really on this kind of problem, the majority of the problem is the setup. But of course, we're not done. Once we have the setup, we want the answer. So we say, okay, well, we've got to work it out. Now there's a couple of ways you could do this one. You can expand it, or you can do some simple substitution if you want. Oh, wait, I see. I need to fix something. It's not a and b, it's 0 and 1, right? Because we go from x equals 0 to x equals 1. Okay, so one way we can simplify this is we can make a substitution. And that's one of our best ways to do integration is substitution. So suppose we make the following. We'll let u equal 3x plus 1. And then what do we have? Well, we have that du is 3 dx, or I can write that as 1/3 du is dx. And then this integral becomes the integral, well, when x equals 0, because these are x bounds, then what does u equal? Well, u is 3 times 0 plus 1, which is 1. When we go to 1, 3 plus 1 is 4. We have the 1/2, and then we're going to get a 1/3, so that makes 1/6. And then we have our u squared du. Now the nice thing is it's a definite integral. We never have to go back. We always keep going forward. And so this becomes, well, integral of u squared is 1/3. So now we're up to 1/18 u cubed. And then we're going to evaluate that from 1 to 4. And we're almost there. So that's 1/18. 4 cubed is 64. 1 cubed is 1. And so we end up with 63/18. Now you might say, well, can you simplify anything? Well, they both have factors of 9 involved, right? 63 is 7 times 9, and 18 is 2 times 9. So if we cancel out a 9, we get our 7/2. And that sounds like a pretty good answer. They might want to say, well, 7/2 what? Do we have any units? And sometimes the problem says give the units, sometimes it doesn't. This one doesn't say give the units, so we don't need to, but it also doesn't tell us what units are. It doesn't say what our measurement for x is, so no units required. And just the final answer, 7/2. Good. So these kinds of problems aren't too bad once you understand, like, what's the goal. The goal is to figure out what does a typical cross-section look like and how do you find the area of that cross-section. It uses lots of words to describe those cross-sections, and so just take them in and say, okay, what does my cross-section look like? How do I figure out my area? And then I can integrate, and life is good. So, all right, good. Well, we're off to a great start already. Let's keep going. Number 2. Let R be the region enclosed by the parabola y equals x squared and the line y equals 2x. Calculate the volume of the solid obtained by revolving the bounded region R around the line y equals -3. All right, so again with these problems, pictures are so useful. All right, so what do we have? Well, we have x squared, which parabola, and 2x. Now, 2x is a line, slope 2. Well, we'll draw something roughly like that. Now, one point that's easy to see where they intersect is at 0. 0 squared and 2 times 0 is 0. So that's great. What about that point? Can we figure that one out? Well, that's saying that x squared equals 2x, or x squared minus 2x equals 0, or x times x minus 2 equals 0. And we're like, yes, 2. Great. All right, so that wouldn't be too hard either to really guess, right? You say, okay, x squared equals 2x. Well, you could have said, look, we want the one that's not 0. divide out by x, x equals 2. All right, so we have this sliver here. Okay, so that's our region R. We've found R. And that's good. Even just finding R is progress. Now, we have to figure out where are we revolving, because that's going to tell us a lot of the story and how we proceed. So we're going around y equals -3. So make sure, you know, is it revolving in this direction or is it revolving in that direction? Because that really changes the approach. So here we're going to go to y equals -3 and we're going to revolve. So that's going to be, if we're using our pens, we're going this way. Okay. Cool. Cool. All right. So we could even try to get a sort of a rough idea of what's happening here and say, all right, now, what is the right technique? What I like to do is think about, okay, how do I slice? Now, everything here is given me as functions of x, so I'm going to think of my little slices here, and I ask the question, what does this little slice do? And in particular, what's the shape that's coming out? Is it a washer or is it a shell? And this particular one is a washer. So we're going to say, all right, we're going to use our washer method. So when in doubt, if you're like, wait, which technique do we use? Think about how you slice. You know, my functions of x are functions of y. Functions of x, vertical slices. Functions of y, horizontal slices. And then what happens to a single slice? The shape tells you the method, washer method. So we say, all right, good. Now we know it's the washer method. And so what is the washer method? Well, the washer method says you integrate a to b. There's a pi, and then it's the big radius squared minus little radius squared, and d, well, whatever you're doing the integral with respect to. So what you have is it's big circle minus little circle. That's the area of a cross section. This d something is the width of a cross section. So this is a little tiny volume, and then you add the volumes up. Okay, so for us, we're going from 0 to 2. That's our a to b. Now, here's where things get interesting, because we're going around -3 and not the axis. So when I'm looking for my big radius, not to be confused with this r for region, r for big radius, I want to go from the furthest out to the line. So that's my big radius. Okay, so how does that work? Well, I'm going from 2x to -3. And I want to ask, how far is that? Well, to find that, I subtract. 2x subtract -3. So we'll just do it this way. 2x subtract -3 squared. Subtract, and we'll switch colors for a second here. My small radius is on the inside. So that's my little radius. And it's getting a little we're stacking things up, but we know what we're talking about here, or as we do it live, right? So it's from the inner part down to -3. So that would be our function. This is x squared part, so that's x squared subtract -3 squared. Okay, and then the d something is a dx, because we're integrating with respect to x. So we drew a picture, we figured out the method, so here's our basic pieces, and we filled it in. A lot of work, and then from here out, it's carrying out the integral, and we just have to be careful. Okay, so what do we have? Integral 0 to 2 pi. Now minus makes a plus. We'll go ahead and expand that. So that would be 4 x squared plus 12x plus 9. Okay, that's the first part. So if you expand 2x plus 3, 4x squared plus 12x plus 9. Subtract, and now here it's x squared plus 3, because minus minus makes a plus, x to the fourth, and then plus 6x squared, and a plus 9. Okay, dx. Well, does anything simplify? Well, yeah, a few things. What do we see? Well, we'll go highest power first. So we have a minus x to the fourth. That's all right. We have a 4x squared minus 6x squared. That makes a minus 2x squared. Well, that's lots of negatives there. A plus 12x. And then the 9s actually cancel. All right, so that's our integral. Well, we carry out this integral, 0 to 2. Oh, whoop, ha 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 ha. We're integrating. We don't need our integral sign, right? Once we've integrated, the integral sign goes away. That's one of those things where if you include it, people are like, oh, I got to take off a point here. All right, pi, and we're going to have minus 1/5 x to the fifth, minus 2/3 x to the third, plus 6 x squared. Evaluate 0 to 2. All right, now we're almost there. We're in our home stretch. We see when we plug in 0, we get lots of zeros, so that's good news. So we just have to figure out, well, what happens when you plug in 2? So we get pi. All right, well, plug in 2 to the fifth. All right, 2, 4, 8, 16, 32. Okay, so that's minus 32 over 5. 2 cubed, 2, 4, 8. So that's an 8 and another 2. So that's minus 16 over 3. And then 2 squared is 4. Don't need my fingers for that one. Times 6 is 24. Well, common denominator would be 15. So let's see, that would be pi. So here I multiply by 3, minus 96 over 15. Here, multiply by 5. So that'd be 80 over 15. And 24, you have to multiply that by 15. Well, that would be a big number. Well, it's not too bad, right? It's 15 times 20 is 300. 4 times 15 is 60. So we get 360 over 15. And, well, okay, so 360, subtract 80, subtract 96. Now, if you put those two together, you're really subtracting 176, right? 96 and 80. So, okay, so I'm an old enough person, I can sometimes subtract numbers in this way. So, okay, carry that leaves us with a 4. 35 subtract 17 is 18, so, okay, 184. All right, good. So we end up with pi times 184 over 15. Now, well, does 15 go into 184 at all? You can check. Well, it's not divisible by 5 because, well, it's not a 0 or 5 at the end. And it's not divisible by 3, 184, because if you add it up, 1 plus 8 plus 4 is not a multiple of 3. And so that's actually as simplified as it gets. And so there we go. That's the answer. 184/15 pi. Cool. Now you might say, did we have to do all that? Well, if you follow the mantra, look, we don't have to simplify, then, and if you're worried, stop there. That's the answer. The rest of it is all just arithmetic. You can say, look, that's the answer. Doom. Done. Voila. I've got it. And so, well, there we go. Okay. Well, another fun problem. And we're just moving right along. So the third problem consider the curve y equals x squared, where x goes from 0 to 3, set up but do not evaluate. This is one of our favorite phrases on any calculus exam. Do not evaluate, because it means, hey, you don't have to do that much work. We really care about setting things up. And oftentimes on a calculus exam, there will be problems, especially when it's applications, where it's more about the setup. Okay, well anyways, back to our problem. We were setting things up, integral, so the length of y equals x squared, where x goes from 0 to 3. Now, y equals x squared, this is our y equals f of x setting. Now, the reason I point this out is there's actually multiple different places where we can talk about length. So we can talk about length in y equals f of x, or in parametric. We can even do it in polar. So we're here in f of x. We say, okay, well, what happens is a little bit of length is found by taking the square root of 1 plus f prime of x squared dx. So here is just a little piece of length. And, well, that's if we want just a little piece, but what do we want? We want the whole thing. And so we add it up. So that is the formula. You see, this problem is really testing us on the formula. And so if we can remember the formula, well, 3 points. And if we can't, we'll just think about like, okay, what's the mantra for applications? The mantra for applications is break things into small pieces, figure out what happens with each piece, and add it up. And if you can remember that, oftentimes you can reconstruct, and if nothing else, it helps like, oh yeah, I remember how that works now. I got this. I can do it. All right, so for us, well, we have our bounds, 0 to 3, and okay, so 0 up to 3, and then we have our square root, 1 plus, and take the derivative. So this is our f of x. So that's f of x is our x squared. So that would be 2x, quantity squared, and dx. And now we stop, right? Because we've set up the integral. This is a problem about setting things up. And so we don't have to actually integrate anything. We just have to set things up. So that's good news for us. Okay, well, let's move to the second part, which is now we're going to set up an integral for surface area. So the surface area obtained by revolving the curve y equals x squared around the y-axis for 0 less than or equal to x less than or equal to 3. Now, okay, this is, we gotta be careful here. Okay, so how does this work? So the formula to key off of, at least the way I remember it, is that you have a 2 pi, then you have a radius, and then you have length. So this is the surface area of a small slice. So the length, by the way, is the same thing as what we saw up in part A. So we know what's going to happen. So how do we finish this off? Well, the key is, what is the radius? So we have our curve, y equals x squared. All right, that's not so bad. And now we say, all right, we're taking a little tiny piece of it. So here's my little tiny piece, and we're revolving. So which axis? This is important, the y-axis. So we're revolving, that's our y-axis. So our radius is how far away are you from the y-axis? And this is one of those things where it's like, oh, if I want to know distance to the y-axis, isn't it just the y? No. It turns out that the distance to the y-axis, is actually x. So that is what goes here. And now we have all our pieces, so the last thing for us to do is write it out. So we still have our same bounds, integral 0 up to 3, our 2 pi, our radius is x, then we have our square root, 1 plus 2x squared dx. And We don't have to evaluate. We have to set it up. We're done. That's it. That's our answer. Ah, I love these problems. Set up and not evaluate. But of course, the key is you have to remember the formulas. And I like to remember the formulas and like, what do the pieces actually represent? Because if you try to remember every special case of every formula, it's too much. It's too much. But if you say, oh, yeah, surface area, there's a 2 pi, a radius, and a length, and then you're like, okay, I just have to, I know what 2 pi is. I use the picture to figure out the radius, and I know the length is that setting. So, yeah. All right, great. Well, we're doing wonderful. This is, we're going to finish with lots of time left. This brings us to number 4. A cubic tank, 10 foot by 10 foot by 10 foot, is completely filled with water at a density of 62 pounds per cubic foot. What is the force acting on each vertical side of the tank? Now, okay, so this is going to be a fun problem. So what's going on here? Well, we have, it's completely full, so that's good news. So we have this tank, and since it's water, we'll use some blue here. Okay, so we have 10 by 10 by 10, and we want to know, well, the water, of course, it's trying to push out, so it's pushing against the sides of the tank, and we have to figure out, well, what's the amount that's pushing? Now the question might be, well, does it matter which side of the tank that we push against? And the answer is no, there's symmetry. So the amount that's being pushed on, say, the front face versus the right face versus the back face versus, it's all the same amount. So symmetry, we only need to know one face, and that's the same, because it's cubic. Each face looks the same. Now you might say, okay, does it really matter that we have the back face if we have the front face? You know, does somehow like the back face somehow maybe absorbs a little bit and cuts in half the pressure in the front? And it might feel like the answer is yes, but actually the answer is no. In fact, it's kind of distracting that there's these extra sides. That has nothing to do with the problem. It's a red herring, and it's trying to throw us off. Because sort of, what's our mindset? Well, our basic setting here is it's about force, right? And so it doesn't matter what's going on. We think about our tank. So let's think about just one side. And as we go down, what's happening, and I feel like I'm getting to my teaching mode. I'm sorry, I just want to remind myself of how this works. Fluid force. So what's going on is at the top, there's just a small amount of force, but as you go down, the force goes up. Now, why does it go up? And the key here is that at a certain depth, what happens is that there's water pushing out, and the reason it pushes out is that all the water on top of this is pushing down. So this is trying to push down, and this water says, oh, I have everything pushing down on top of me. I want to try to get out. So it's pushing out. The further down you go, the higher the column of water pushing from above, and so the more it pushes against the side. So there's the depth going that as you get deeper, the amount of pressure against the side, which is going to relate to the force, goes up. Okay, so how do these formulas work? Well, so for this, we're after a force. We say, well, okay, the force is we're going to go, and we have integral a to b. There's the density. There's the depth. There's the area. Those are the pieces that come into play. Now, one thing that you can use to convince yourself, is this formula right? And this is something I normally don't do, so don't tell anybody that I'm doing this. Shh, just between me and you, right? Is think about the units here. So the density, this would be a pound per cubic foot. The depth would be foot. The area, well, that's foot squared. And if you multiply this all out, what happens is you get pounds. And that is a measurement of force. So that says, okay, good. We might be on to something. Okay, so here's the basic idea. Now, when I talk about area, what I mean is I'm slicing at a fixed depth. So this is a little slice here. And, well, we like to set up units so that things work well. So the way you set up units in these kinds of problems is the water level, you set a depth to 0, and then we go down. So when we have our integral, we're going from 0 to 10, because 0, the top of the water, down to 10, and that's how far the tank goes down. The density is 62. Constant density. All right, well, why? Well, because it just says density is 62. There's no variable, so it's always the same. Now the depth, that's how far our slice is. That would be x. What about the area? So the area here, this is where we have to look at our cross-section. Now, in this case, we have a width of 10, and a height is dx. Now here we're taking advantage of the fact that we have a square. And so it's always the same width, and the height is where the dx comes in. So we say, oh, all right, well, this integral doesn't look scary at all. And indeed, this isn't meant to be a scary integral. It's basically, the key is, can you set things up? All right, so we're most of the way there. The integral of 620x, well, you x squared over 2, so you have a 310, and then x squared, because, you know, that's 620 over 2. You go from 0 up to 10, and plug in 0, you get 0. Plug in 10, well, you just add some zeros. In this case, you're going to add 2 more zeros, and you get 31,000, and our units is pounds. And this, we make a note, this is true for each side. 31,000 pounds. And that's it. That's the answer. Not too bad if you remember the setup. And again, that's a lot of the work. It's just remembering, how do you set it up? And so practice, right? Make sure you're comfortable with all these problems, because there's probably going to be a force problem, or they love work problems because they really like to see us work. And so make sure you're comfortable with both those problems. Number 5, find the x-coordinate of the center of mass of the thin plate of constant density delta located in the first quadrant, bounded from the top by y equals 1 and from the bottom by y equals x squared. You may use the fact that the mass of the plate is 2 delta over 3. Okay, wow. All right. Well, there's a couple of things, of course. We see right away it's a center of mass, and we know we're looking for the x-coordinate. And so we say, okay, well, let's remind ourselves of a couple of things. That the x-coordinate for the center of mass is found by my over m. Now, my is the moment, and in particular, it's the moment with respect to the y-axis. It's kind of this one kind of like counterintuitive things, like, hey, if I'm looking for the x-coordinate, I look m sub y. If I'm looking for the y-coordinate, it's m sub x. And the m, well, that is the mass. Now, the nice thing is we know what mass is without any work, because they told it to us. So mass is 2 delta over 3. Good. All right. So now we say, all right, that's our basic formula. And, well, what does our region look like? Because we should know that. That's going to probably have something to do with our answer. So we'll sketch it really quickly. A quick little sketch. We have to stay in the first quadrant because it says the first quadrant. The top is y equals 1. the bottom, y equals x squared. And, well, y equals x squared, very popular on this exam. And so, we say, all right, great. So, our little thin plate has that shape to it. All right, okay, so now, what do we do? Well, we do what we always do, right? We say, hey, let's think about what happens when we take a small little slice. And in fact, how do you compute the moment? So if you think of the way you do moment, how does it work? Well, what you have is you do a combination of two things. It's the mass times distance. That's the moment of a little piece. And then the total moment is you add it up. Now you can go a little bit more precise. You can say, well, what's mass? Well, mass is your density. And then here it's a two-dimensional thing. So it's an area and our distance. Okay, so those are the pieces. So that's our basic formula. So now we just have to go through and say, all right, let's figure out all these little pieces and we can find our moment. All right, so for us, let's work through this. M sub y. Well, our shape here, we're going to go from 0, and, well, when does x squared equal 1? Is that 1? So we're going 0 to 1. Our density, that is our delta. So delta. Our area. So here's our little slice. The thickness is our dx. Okay, so, okay, density there. And our height is going to be from the top to the bottom. So it's 1 minus x squared. And I like to put the dx at the end. So our 1 minus x squared dx, that's our area. And our distance. Well, the center of mass is there, and we want it to the y-axis, so it's how far away is the y-axis. And the distance to the y-axis is x. So there's an x, and that's what goes there. So there we go. There's our moment. Yeah, the moment. That's what I didn't mean to say that. Ha! Whew! Good. Our moment with respect to the y-axis. And so now we need to compute that. That'll give us this term, which we combine with what we already have been told, and give us what we want, our answer. All right, so here we go. Well, we can pull out a delta. We have the integral 0 to 1. We can pull it out because it's a constant. X distributes, so we get x minus x cubed. All right, so that's delta 1/2 x squared, that's the integral of x, 1/4 x to the 4th, that's the integral of x cubed. Evaluate that from 0 to 1, and well, the good news is that's not so bad. Plug in 0, we get zeros. Plug in 1, we get 1/2 minus 1/4, and that is 1/4 delta. Now that's not our answer, right? Be careful. Oftentimes when we do something big, we're like, woohoo, we got the answer! But no, this is our step to find the answer, because now we have the numerator. Okay, so our real answer, x bar, would be the 1/4 delta, which is the m sub y, over the 2/3 delta. So remember, this is our, we'll go ahead and write it again, my, and this is m. Now you notice the deltas cancel. And that makes sense, because if I'm uniform density, it shouldn't matter how dense I am. That won't change my center of mass. So if my density is 1 and my density is 10, I won't have a different center of mass. So that's good. That makes sense. And, well, okay, so we can cancel the deltas. This is also the same as 1/4. 2/3 comes up, as 3/2. And so we end up with 3/8. Good. So where is that? Well, 3/8 is a little bit below a half. And so if we were thinking of our picture, a half would be roughly halfway. So 3/8, maybe it's roughly here. And it's good to just sort of see, is that a reasonable thing? Is that where the center of mass is? And 3/8 seems pretty reasonable. It feels like we should be less than a half, but we definitely shouldn't be negative. If we got a negative, we're like, no way can the center of mass be over here if all the shape is over there. If we got an answer like 2, same thing. We know we're wrong. But 3/8, that's a reasonable answer. And it's okay to check, is something reasonable? And there we are. 5 problems done. Woohoo! All right, we're in the home stretch. 2 to go. Number 6. Consider the parametric curve. X is 1 plus cosine t plus cosine 2t, and y is sine t plus sine 2t. And they even said, hey, if you use your double angle identity, sine 2t is 2 sine t cosine t. And so you can pull it out. That's the same as sine t times 1 plus cosine 2t. And all right, so we're told those are our parametric curves, and negative pi is less than t, less or equal to pi. Now, what does this look like? I don't know. It's kind of hard to do parametric curves. We're not used to it, but maybe we don't really need to know. And it says, okay, give the equations with y as a function of x for the tangent lines to the curve at the origin of the Cartesian coordinates. All right, so when are we going to be at the origin? Well, so let's start with there. Origin is 0, 0. And now, okay, so we want to be at 0, 0. And we say, okay, how can that happen? Well, we have to have y equals 0 and x equals 0. And, well, we have 2 equations. Now this one, they've already factored it for us. So say, oh, okay, let's start with that. So we need to have y equals 0, which is sine of t times 1 plus 2 cosine of t. And we start asking our questions. For instance, when does sine of t equal 0? And if we plug that in, that would be at t equals 0, which is in that range. And even at t equals pi, because if you remember your unit circle, and who doesn't, classic, the sine is the y value, so that would be at these 2 points. And so that's at 0 and pi. Negative pi isn't in our interval. Now, I'm not claiming that this works. I'm just saying these are candidates. What about the other one? Well, this says we need cosine t to be negative a half. And we say, when can that happen? So cosine is a y value, and so that would be, if we're over here, and maybe I'll switch colors for a second. So we'd be looking for these angles. And we're from negative pi to positive pi. So we say, well, what is an angle that does that? And if we figure out one, we can get the other. Now, once you kind of know that there's only certain angles, so pi 6, pi 4, pi 3, you kind of can almost eyeball it in. Say, well, roughly, that looks like about 60 degrees coming off of that axis, so that may be like 120. And then we say, oh, but wait, we're doing calculus type things. So, oh yeah, calculus type things, yeah. Okay, in that case, we would say that that would be at 2 pi thirds. And then our other angle here would be at negative 2 pi thirds. So there's 4 candidates. Well, which one actually works? To figure that out, we come to our x of t. Okay, so what is x of 0? Be 1. Cosine of 0 is 1. Cosine of 0 is 1, which is 3. Nope, doesn't work. How about pi? X of pi. Well, that would be 1 plus cosine of pi is negative 1. Cosine of 2 pi is positive 1, which is 1. Out. That's not going to work. Okay, well, how about x of 2 pi over 3? Okay, well, what's that going to be? So we're going to get 1. Now, cosine of 2 pi over 3, we actually know that. That's negative a half. Cosine of 4 pi over 3 would be where? Well, it's the same as cosine negative 2 pi over 3, so it's also negative a half, which is 0. So that's good news. So that one does work. What about negative 2 pi thirds? Now, you might think, this is going to be hard, but then you remember something. Cosine is even. So whether I plug in a positive or a negative doesn't change the response. So I'd still have 1, negative a half, and negative a half, which is still 0. So our great aha is we now know the following. We want to find the tangent lines, and really the slope of the tangent line at t equals 2 pi over 3 and negative 2 pi over 3. And the good news is this is a point on our tangent line because it goes through the origin. So that's why we only need the slope, because we already know our point. So our answers are going to be y equals something x, y equals some constant x. We're going to have 2 answers. All right, well, here we start going. So let's think, how do we find slope? So slope, that is our dy dx. Rise over run. Change in y, change in x. All right, well, that's not so bad. So how do we find that in terms of using derivatives? Well, for parametric curves, that's dy dt over dx dt. You can think of it as like the dt's cancel. And you say, oh, okay, so what is that? Well, so we take derivatives. And so the derivative of 1 is 0. Derivative of cosine minus sine. Derivative of cosine 2t would be minus 2 sine of 2t. All right, that's our dy dt. I do this all the time. This is a classic Steve mistake. So I know that I do it often enough that I catch myself half the time. It's so tempting to say, well, we put the x of t first, so that should go in the numerator, right? But no, they switch roles, they go out of order. All right, don't make the classic Steve mistake. Do the right thing. Okay, so let's try that again. Okay, so the numerator, dy dt. Start with the derivative of y with respect to t. Derivative of sine is cosine. So we have cosine t. Derivative of sine 2t is 2 cosine 2t using the chain rule. Downstairs, the 1 goes away. Derivative of cosine, negative sine. And derivative of cosine 2t minus 2 sine. Okay, good. So now we just need to make a couple of notes here. And all right, so what's our notes? Well, we should write some angles here. So I'm going to go ahead and list some angles. So we know cosine of 2 pi over 3 is negative 1/2. Cosine of 4 pi over 3 is still negative 1/2. So if you go to the circle, 2 pi over 3 is here, 4 pi over 3 is the one down here. Sine of 2 pi over 3, well, that is what's our y value here? So if we have our x value is negative 1/2, Pythagorean identity, sine squared plus cosine squared equals 1, and we say, oh, okay, well, then we got the cosine is 1/2 squared, it's 1/4. Sine squared should be 1 minus 1/4. which would put it at positive square root of 3 halves. And then sine of 4 pi over 3 will be at negative square root of 3 halves. Okay, so all of this is to say we get the following. This is really testing our trig knowledge, isn't it? Yeah, sometimes they do that to us. Okay, so at 2 pi over 3, we have our slope is, well, plug things in. Cosine 2 pi over 3 is minus a half. 2 cosine of 4 pi over 3 is, again, minus 2 times minus a half. Sine of 2 pi over 3 is going to be minus square root of 3 halves. And then we have minus 2. Sine of 4 pi over 3 is minus square root of 3 halves. Now, since everything has a half in it, we can actually just go ahead and cancel all the halves. So we'll just cross those out really quick. And what do we have upstairs? Well, we have minus 1 minus 2 makes minus 3. Here we have minus square root of 3 plus 2 square roots of 3 makes a square root of 3. And, well, 3 is square root of 3 times square root of 3, which gives us a minus square root of 3 as the answer. Now, 4 pi thirds, do something similar. Well, what happens? Remember, we said the cosine is, 4 pi thirds, should be negative 2 pi thirds. It's the same angle, but, all right, at negative 2 pi thirds, remember, we said cosine was even. What about sine? Sine is odd. So, when we plug things in, the only thing that changes is the cosine keeps the same sign, but for the sine, it flips. So, again, you can cancel off 2's. You say, oh, we have now upstairs, we have minus 3. And downstairs, you have a plus root 3 minus 2 root 3, which is a minus root 3, which ends up, the minuses cancel. 3 over root 3 is a square root of 3. All right, so we're in our home stretch. What do? Well, we know our point is 0, 0, and so our lines have the form y equals some constant x, the constant being the slope, and so our answers are y equals minus square root of 3x and y equals positive square root of 3x using our slopes. And that's it. Wow, that's the answer. We wrote down a lot, but most of what we wrote down was just sort of trig things. And so if you're comfortable with your trig, you'll be okay. And if you're not, well, you still have some time, I hope, before the exam. So it takes some time to get a little bit comfortable. But there we go. Those are our desired tangent lines. Plus and minus square root of 3. Nice. Number 7. Find the area inside one loop of the polar curve r equals 6 sine 3 theta below. And they even gave us the picture. And it's like, okay, we want to find that. Cool. Cool. So, well, what do? Well, what we need is a couple of things. We know what's our formula for polar. So for polar area, what do? And the answer is we integrate alpha to beta, because it's not a to b, there are angles involved. So integral a to b, alpha to beta, 1/2 of your r of theta squared d theta. Okay, so that's what you need to integrate. And say, okay, well, great. So how do we do that? Well, all right. So what do we need? Well, we need to know our r of theta, and, okay, we found it. That's what goes here. 6 sine of 3 theta. Well, that wasn't too hard. And then the alpha beta. All right, so how do we figure that? Well, we can use the picture to sort of help guide us. And we say, well, there's an angle here, there's an angle here. And that sort of gives a clue, right? Like, it looks like an angle of 0. Eyeballing it, pi thirds maybe? I don't know. Let's not eyeball it. Let's get it right. So we say, okay, if I want to know, we say, when does it hit the origin? In other words, when does it r equals 0? Well, the 6 doesn't matter, so just get rid of it. And now we say, well, when does sine equal 0? Now, the first time sine equals 0 is at 0. The next time is at pi, and then at 2 pi. It turns out it's really the multiples of pi, right? And, of course, we could go negative, but we don't need to. Well, so that's when sine equals 0. So we say we want what we plug in to be either 0 pi, 2 pi, or 3 pi. So that says, oh, so we want 3 theta to be one of these. So that says theta, when it happens, is 0, pi over 3, 2 pi over 3, and so forth and so on. And we say, so 0, okay, that's the one we see there, and pi thirds. That's this one. 60 degrees. That looks right. So, good. We're cooking now. We're cooking with gas, so to speak. So, we now put it in. Say, okay, our area is going to be the integral 0 up to pi over 3 of 1/2 our 6 sine 3 theta squared d theta. And remember, the whole r expression gets squared, including the 6. So 6 squared is 36 divided by 2 makes 18. So we have an 18. We'll pull it out for the moment. 0 to pi over 3 sine squared of 3 theta. Say, all right, so we're almost there. If we can figure out how to integrate sine squared. Well, it's not one of our basic formulas, and there's a reason for that. We say, hey, you can rewrite trig functions. In fact, that's the big thing about trig. It's not a curse that you can rewrite trig functions. It's actually a blessing. It's why we spend so much time learning the identities, learning how to rewrite things. So for us, we say, well, we rewrite sine squared. And we go back and we say, well, is there an identity? And it turns out there is. Sine squared of x, or it doesn't really matter, but we'll call x, is equal to, this is called the power reduction, 1/2 1 minus cosine of 2x. So, when in doubt, try a couple values. It's like, okay, when I plug in x equals 0, I should get 0. And that's how you can know whether it's a plus or minus. All right, so in our case, for us, we say, our x is our 3 theta. So our 2 times x is going to be 2 times 3 theta, or 6 theta. So what do we have? Well, okay, so we have a half. That can join our 18 out front. So that makes it 9, integral 0 to pi over 3. And then we have a 1, subtract cosine 6 theta. Okay, so we can now integrate. So we have a 9 in the front. We'll have theta. And then the integral of cosine is positive sine. And so positive sine 6 theta. But we have to account for the 6. So that becomes 1 over 6. And evaluate 0 to pi over 3. All right, so we'll have 9 pi over 3. And then we have sine of 6 times pi over 3 is sine of 2 pi. Well, sine of 2 pi is 0. Okay, well that's nice. Subtract, plug in 0. Well, 0, sine of 0, 0. So, okay, 0 minus 0. So, well, finally, pi thirds times 9 leaves us with 3 pi. Easy as 3 pi. Well, wait, not quite that easy, right? But not too bad, not too bad. Polar problems are lots of fun. It's a great chance for us to show off our trig identity skills. And yeah, you can pretty much count on those. They love polar problems. And all right, well, that was it. Number 7, that's our last one. I want you to know you can do these things. Applications, I know there's a lot of information here, but just think about, break things down, understand the formulas aren't just, don't memorize tons of special cases. What do things represent? And how do they fit together? And when you do that, it becomes a lot easier. You can do this. I believe in you. And I hope you do well. All right.